Okay, it's time to start the spring semester ITC lunches, and although it doesn't look like spring, I can guarantee the spring will come, and we didn't have a bad winter so far, and we very much look forward to a lot of exciting discoveries in the coming months. We just heard a fantastic talk by Ryan and MacDonald with a lot of exciting new results that we very much look forward to your success with new JWST proposals, further analysis. And we'll hear more from him in a few minutes. We'll start with Akos Bogdan, who is here, who will tell us about the line emission mapper probing the physics of cosmic ecosystems. And then we'll move on to Itamar Allali from Tufts, not very far away. He will tell us about stepped dark sectors phase cosmological data. So, as you know, there are at least 2 dark sectors, maybe more, and now the data constrains them, so that's what we'll hear about. And then from our own Amir Siraj, where's Amir? Oh, here it is. Very accomplished undergraduate here and also at the New England Conservatory. He played with Yo-Yo Ma not so long ago, and he will tell us about some of his most exciting scientific discoveries recently to do with interstellar meteors. We're planning, in fact, tomorrow there will be a meeting with the funder of this expedition that relates to what Amir will discuss, looking for the first interstellar meteor in the Pacific Ocean. And then finally we'll hear from Ryan MacDonald that we heard from, and he will tell us about fitting your first exoplanet spectrum in less than 10 minutes, which sounds impossible, but is it on the iPhone? Do you have an app or something? Okay, so let's start with Akos. Go ahead.
Awesome. Thank you very much. It's my great pleasure to talk to you today about the line emission mapper. And although I'm giving this talk, I should mention that I'm giving this talk on behalf of a large team. So this comprises over 200 scientists and engineers who are working toward the success of LAM to make it a reality. So what is line emission mapper, or LAM for short? So this is a mission concept for the NASA 2023 Astrophysics ProBAO. So the proposals for these $1 billion cost cap missions will be due later this year, so sometime in September or October. And I should also mention that CFA is the host institution is the PI institution of LAM, and the PI is Ralph Kraft, our very own Ralph Kraft. So before going into details and telling you about landscape and anything else, let me just show you a very important plot, a key plot. So let me see if I have a laser here. No. Okay. So this is a simulated LAM image. Okay, no laser. So this is a simulated LAM image on 1 megasecond deep image of a Milky Way type galaxy, so roughly 10 to the 11 solar masses galaxy. And the left side of this image shows a very narrow band X-ray image around the oxygen 8 line. The right image shows the same image, so a similar image, but on the iron 17 line. So very narrow 2 eV broad image. And this is why we need high spectral resolution. So LAM is a wide field, large area, high spectral resolution X-ray imager. Okay, and it will make spectrum and images. So it's essentially an X-ray IFU. So the key point of this image that we will see with LAM the extended hot X-ray emitting gas out to very, very large radii, well beyond the stellar disk. So on the left image, you see a tiny, tiny blue ellipse. So that shows the rough size of a galaxy disk. So this is more up until now, and with Chandra-X, and we have been limited to study really the innermost parts of the gas, of the hot X-ray emitting gas. With LAM, we will be able to study really out to the R500 radius and beyond. And we will be able to see all these beautiful structures. So here in this particular example, we selected a galaxy which shows a feature, similar feature to our very own Fermi bubble. Okay. So let me just give you a few words about LAM. So LAM is really focusing on the cosmic ecosystem. So this is the primary theme of LAM. And the goal of LAM is to transform our understanding of the formation of the cosmic structures over 6 orders of magnitude, all the way from the parsec scales up to megaparsec scales, so essentially tracing the filamentary structure of the universe. The key goals, one of the key goals and part of the directed science program will be to map the galactic halos, just like I've shown you before, over a range of masses, so from low mass galaxies to more massive galaxies, which will provide a key missing link in our understanding. Additionally, LAM will also perform a shallow all-sky survey, so we will study our very own Milky Way in much detail. So we will map the gas flows, we will map velocity of the Milky Way gas flows. It will also map on larger scales, as I mentioned, also map the intergalactic medium or filamentary structure of the universe. And on top of that, it will map star-forming regions, supernova remnants, Fermi bubbles, and of course our own galaxies I mentioned. What is very important is that LAM is an X-ray IFU. So because of its unique features, the key science goals of LAM cannot be performed with CCD imaging, so what Chandra and XM Newton are doing, or grating spectroscopy. Okay? Because the key goal of LAM is to map the diffuse emission. So on this image here, you see a CAD drawing of the line emission mapper. So this is coming from our industry partner, from Lockheed Martin, and it is a simple concept. X-ray mirrors on one side here, and the instrument, the microcalorimeter array, is on the other side of the instrument. So as I mentioned, PI institution is CFA, so PI is Ralph Kraft, and LAM was conceived to study large-scale, low surface brightness diffuse X-ray emission in the soft band. So this is 0.222 keV band. It has large field of view, and thanks to its large field of view, so half a degree times half a degree field of view, it can really study these extended faint features in a single pointing, so nearby galaxies in a single pointing, so there will be no need to mosaic these nearby galaxies. It will have 15 arc segment pixels, and thanks to the dithering that LAM will do, it will have a 10 arc segment angular resolution. So essentially what we will have is XM Newton kind of imaging, so XM Newton with larger area, but with 50 times better spectral resolution, and that is the key. So LAM, when it will fly, it will go to L1, most likely, which will provide us 90% observing efficiency. And very importantly, I cannot stress that enough, I'm not going to focus too much on the guest observer program. Very importantly, LAM will open an enormous discovery space for guest observers. So LAM will spend most of its time, 70% of its time for guest observer programs. So let me just illustrate this whole story about CGM and hot gas with a video. So this is a TNG galaxy, TNG 50 galaxy, and what you can see here is that this hot gas is really extending to large scales. So the side length of this image is roughly 500 kiloparsecs, half a megaparsec. So the hot gas, this AGM feedback is pushing out all the hot gas and metals and out to very large radii. So up until now, we just couldn't see the hot gas, right? On the corner, you see a galaxy to scale. So we were really limited to the innermost regions, and we could never study the gas to such large radii. Why X-rays, you might ask? Well, we need X-rays because for Milky Way type and more massive galaxies, the bulk of the gas, so the dominant fraction of the gas is really in the X-ray phases. So you see here the red and the purple curves show the column densities for oxygen 7 and oxygen 8, both of which emit in X-rays. So oxygen 7, which is traceable by UV, of course the COS-HALOS studies have made enormous progress with that. They are very important for lower mass galaxies, but for more massive galaxies, we really need to study the X-ray gas, and this is where LAM enters the picture. So, as I mentioned, LAM is an X-ray IFU that will map the CGM halos. So let me just show you on this top left image. I show you a traditional broadband image. So this is a notional, this is not a Chandra image, this is again a simulated galaxy, 1 megasecond deep observation. This is a notional image of what we would get if we had a large area telescope, similar to Chandra. So imagine it as a super Chandra, for example, right? Super Chandra, or it's better to say super XM actually because of the spatial resolution. So this is a 0.322 keV band image. It's a broadband image. This is what we typically deal with. You see all these point sources. Do you see the gas? No, you don't see the gas. because this is dominated by the Milky Way foreground emission, and I'll show you in a second why is it such a big issue, the Milky Way foreground emission. You see all these point sources there, right? So those are cosmic X-ray background sources. This image shows the optical image of the galaxy, so it's really small. The optical emission is coming from a small region. No surprise there. If you take a very narrow band image, again, a 2 eV broad image, at the oxygen 8 energy, you immediately, this hot gas extending out to the R500 radius and even beyond just pops out. The same with the iron 17 image, so you can really study the structure. One important and interesting thing is that I didn't mask the point sources here, right? What we have done, we essentially spectrally excluded them. So the energy range that we study here is so narrow that the point sources essentially don't contribute at all. Okay? We didn't do any trickery here. So what LAM will do, LAM will really study the CGM structure in these very narrow energy lines. It will measure the density, of course, in the inner parts. It will measure density, temperature, and velocity of the gas. And overall, when we combine all of this, then we are confident LAM will complete the picture of galaxy evolution. So let me just illustrate this whole narrow band imaging and spectra and everything what I was talking about so far. So here is an example, a simulated spectrum. Okay, it is a LAM spectrum with 2 eV spectral resolution, so 50 times better than what we have nowadays with Chandra and XM Newton, which can be seen with the green curve. So this is the CCD resolution. What you see there are these blue spectra are the Milky Way foreground lines. So this is gas in our very own galaxy. Okay, if we place the galaxy at a redshift of 0.01, which is roughly 40 megaparsecs, then the lines coming from this external galaxy at redshift 0.01 will redshift away from the Milky Way foreground lines. Okay? So you see those lines, the blue lines there, are absolutely redshifting away. So thanks to the high spectral resolution of LAM, we can separate those lines. We can separate the emission associated with the external galaxy's lines from the Milky Way foreground lines. So essentially, we are dropping the signal, or we are increasing our signal-to-noise ratio by a factor of 50, factor of 100, okay, by a huge factor. And then we can make images in these narrow energy ranges. Okay, I need 2 more minutes. So LAM is also will be able to probe the cosmic web. So this is the intergalactic medium, which is the repository of all the metals ejected from galaxies over their lifetime. And again, this is the same deal. Here I show this is a simulated image on the bottom, and on top you have a very nice spectrum of a galaxy, and you see those tiny little bumps. Those are the signals. Those are the oxygen 8 and iron 17 signals coming from the filamentary structure of the universe. And you absolutely need LAM. So with grating spectroscopy, you can tell that there is gas present, but you cannot map it. You cannot really characterize in a way that LAM will be able to do. As I mentioned, LAM will do a shallow all-sky survey, and with this, we will study the black hole feedback in our own galaxy. So this is the best way to study black hole feedback at the highest resolution. So at 100-second depth, so this is a very shallow survey, we can, which can be done in a few months of observations, roughly 3 months of observation. We can integrate some areas, so this is a spectrum for 10 by 10 degree area, so we can really study these very narrow emission lines, and we can map how the gas is flowing in our own Milky Way. So 70% of the time will be spent with guest observer science. Okay? That is very important part of the probe AO core, is that bulk of the time will be available for the community. So if your favorite science is not CGM, but anything else, I'm pretty sure you can find it here. Okay, so this is just a big list. We have working groups in all areas of astrophysics. So if you want to study high redshift AGN, you will be able to do that. If you want to study protoclusters or high redshift groups, or even planets, we have a working group for planets, right? So, and of course, we are expecting a huge number of unexpected discoveries. So this is my concluding slide. So overall, we are confident that LAM will deliver paradigm-changing science in the area of cosmic or formation of structure. And we are also hope to provide the entire astrophysics community a new and powerful tool that will transform all areas of high-energy astrophysics. LAM will fit into the $1 billion cost cap, so all probe missions have a cost cap of $1 billion, excluding the launch. And what I also wanted to mention is that if you are interested to LAM and you want to learn more about LAM, we will have a science workshop here in this very building and then in this very room in Philips from February 28th to March 3rd. And all of you are welcome to sit and enjoy discussion. So if you want to learn more, you can find the link here. So that's all I have. Thank you very much.
Thank you, Anush. As it happens, today on the archive there is an annual review of astronomy and astrophysics about circumgalactic gas. So that would be advertisement for the kind of science you were describing, and it's written by a former student here, Bogdan, together with Peng Ho. So I recommend it. It's quite a thorough study of the physics associated with what you were describing. But the question is, what is your forecast, the political aspect of this? When do you expect this to be evaluated and so forth?
Yeah, so the timescale, as I mentioned, so the actual call will be put out sometime in the summer, around July, and then the proposals will be due 90 days after, so on the September-October timescale in 23. Then there will be roughly 9 months of time of deliberation, so when NASA makes a decision, which missions go to phase A. So there are currently, I think, 5 X-ray missions. So the probe call, in the probe call fire, it will be either fire or an X-ray mission competing. So there are 5 X-ray missions which are competing against each other, and of course against the fire missions. So phase A will be done. Phase A selection will be done sometime in 2024 summer, and then again we have to write a phase A proposal, and then ideally this probe mission will fly in 32, so in 9 years from now. So it is a very, very tight schedule, so there is not really time for technology development.
But it's good you have NASA on your side here. Any questions? Go ahead.
Just for clarification, the 2-electron volt resolution, has that been demonstrated in the lab, or is that a developmental goal?
Excellent question. You are calling for one of my backup slides. Thank you very much. We didn't discuss this before. So this is a very recent, it's like a couple of weeks ago, a recent test of individual pixels and also these hydras, which are these couple pixel arrays, right? So these are 4 pixel arrays, sorry. I wanted to do this. And so these are recent lab measurements of individual pixels on the left and these hydras on the right. So as you can see, these are perfectly demonstrating the predicted energy resolution. So 0.9 eV for this inner subarray. So LAM will have a subarray with 0.9 eV and 2 eV on the right for this hydra. So this is the goal. So yes, this has been demonstrated, and this is a very, very recent, couple of weeks old result.
Other questions?
Behind you.
No, go ahead.
Sorry if you said this. I was wondering out to what redshift you expect to detect CGM, and kind of related, are you worried about particular velocities when separating Milky Way foreground?
So what we are doing and what I've shown in this particular case, so this spectrum is done at redshift 0.01, and the reason for that is that the strongest line essentially is the oxygen-7 forbidden line, which is the left line of the oxygen-7 complex. So as you can see in this particular spectrum, the oxygen-7 forbidden line redshifts away from the Milky Way foreground complex at redshift 0.01. If you want all 3 of these lines to redshift away, then you have to put your galaxies, or you have to select a galaxy which is at redshift roughly 0.035, so 100 something megaparsecs. So for bigger galaxies, of course, they have bigger R200, R500 area, so they are going to field of view with emission, with detectable emission, even at redshift 0.035. So these less massive Milky Way type galaxies, we will probably study them at redshift 0.01-ish. Does it answer your question?
Yeah.
Okay.
The second part of the question was about velocities, but this is like 3,000 kilometers per second, which is even more than supernova ejecta kind of.
Yep.
So you're safe on that particular velocity side. Any other comments? If not, let's thank Akosh.
I don't know.
All right. Okay, thanks. So my name is Itamar. Thank you so much for having me. It's really great to be here from about 2 T-stops up the road. Today I'm going to talk about this developing story about cosmological tension and cosmological data, and I'll be talking about some models, and in particular getting to these stepped dark sector models. So that's a quick overview, so let me just jump right in. Okay, so this is not news to anybody, but we have a great description of cosmology. It's the lambda CDM model. It works beautifully well. You can think of it as this 6-parameter model with these or other parameters based on how you like to describe it. And as an example, it fits Planck data exceptionally well. Importantly, it agrees with other data as well, in particular baryon acoustic oscillation data, large-scale structure data. Lambda CDM, as fit to Planck or other CMB data, is just a really nice picture, except for you've heard about these tensions as of late, maybe too much now, maybe you're sick of it, but at least the Hubble tension I think everyone in the room has heard of, but it's this notion that if you take a local measurement of the Hubble rate, you find something quite faster than what you infer from CMB. So in particular, the Shoes collaboration, they use type 1a supernovae calibrated by Cepheid variables, and what they find is now a 5 sigma, basically, discrepancy with Planck. And maybe you've heard a little bit less about this, but there's also a tension in large-scale structure data, in particular, cosmic shear surveys locally measuring the matter power spectrum of matter clustering today disagree with how we infer it from CMB. It's much milder, around 3 sigma, but something to be taken seriously. Okay, and so really quickly, let me go over some favorite solutions. You may have heard of early dark energy as sort of the most studied and most discussed solution. It certainly works well for the Hubble tension. An important point about this model, though, is that from a particle physics perspective, it doesn't have a clear realization. It's a very good phenomenological model, but the particle physics is tough to pin down. And also, another important point I want to bring up is how it is evaluated by large-scale structure data, which importantly is in agreement with Planck when you look at lambda CDM. But looking at these posterior distributions, for example, the gray sort of shows the success of solving the Hubble tension by this model, but the red and the blue are when you add in the large-scale structure data, and the ability to accommodate large H0 is affected significantly. And another point is that when you do, even if you don't include large-scale structure data directly, you just fit to this model, you get an increase in the matter power spectrum exactly on the scales that are measured by these surveys. And so the S8 tension, the large-scale structure tension, is worsened. So this is sort of old news. It's been discussed by several people, but it remains something that needs to be addressed, that sort of these two tensions in cosmological data are at odds, and solving them together is a bit tough. So something that my collaborators and I did a little over a year ago is we found that if you take something like EDE, although in our model we parameterize it a little bit differently, but you add an ultralight axion dark matter component to this otherwise, lambda CDM with most of the dark matter being cold dark matter, you're able to do better. So what happens is if you have an ultralight axion which is very, very light, something like 10 to the minus 26 electron volts, the lightest ones that you might consider as dark matter before they start behaving like dark energy. And these are, of course, very, very heavily constrained by data. But even so, within that small amount of dark matter that you're allowed to have, you get to sort of destroy some structure formation on these small scales, which are probed by these large-scale structure surveys. So maybe the most important thing to see in this plot here is that when you include priors, so the shaded curves include priors on the Shoes measurement of Hubble and measurements of S8 from large-scale structure surveys, lambda CDM isn't really able to accommodate these values, whereas this decaying dark energy plus an axion does. So that's nice, but it still leaves some questions. Doesn't really answer the question of why, how you get early dark energy from particle physics. And so for the remainder of my time, what I want to focus on are these step dark radiation models. So this is a bit particle physicsy, but I'm going to try to not focus on any of the details. The idea is to do the following: take lambda CDM, add a dark radiation species. Now this has been done by many authors, but in 2021, this Dan Allali and Martin Schmaltz and Melissa Joseph, their collaborators, they came up with this model where instead of having just a light species, which is decoupled from the standard model, you have a step in the abundance of the species. And you can get this in a few different ways. And at least phenomenologically, the parameters of the model are its abundance, the redshift at which the step occurs, and then the size of this step in the abundance. And what's really attractive about this model, and perhaps isn't really highlighted enough, is that it has really simple, straightforward particle physics. So in particular, you can get this by just having two light species and some additional dark sector. They can be really boring, and one of them acquires a mass, or it could have been massive all along and it just was too relativistic to care, and then once its mass becomes relevant, it decays into the other one. And this is a very simple construction, and it gives you this phenomenology. And in addition, in a sort of update to the model that they came out with last year, they add interactions between this sector and the cold dark matter of lambda CDM. And so sort of getting to the punchline is that this model does well. If you compare it to lambda CDM, you see a plot very similar to the one I showed about the model that I developed. It gets into that cross region between the shoes measurements and the large-scale structure survey measurements. And that makes it attractive because not only does it do well at fitting to the data, it also has a good particle physics realization. So what we wanted to do, and what I want to show a little bit, is very preliminary results, which I'm hoping are going to come out in like the next 2 or 3 weeks or so. But we want to test it against the large-scale structure data because this was sort of an issue for early dark energy. It was one of its downfalls, in my opinion, and so this is an important point for this model. And in particular, one thing that you want to look for is when you add in large-scale structure data, does it decrease the ability of this model to actually solve things by further constraining the abundance of this species? So what I'm showing you here is a posterior distribution so D is a minimal data set, which is just basically Planck data plus Pantheon supernovae data and BOSS data, BAO data. And then if you just add in large-scale structure, which is the orange curve, it doesn't really change the posterior. If you really are into looking at the statistics, you can see, oh, one of those two distributions is peaked, the other one is not, but they're very similar. But to solve the tension, you need to be somewhere in this green distribution, which is the one that is preferred by these local measurements. And so it sort of says, okay, this could work, but these two distributions are sort of not in great agreement. But this at least doesn't kill the model. And in this view, it's interesting to see as well that if you look at the shaded blue curve, which on this plot, this doesn't include the direct measurements of H0 from shoes or the S8 measurements. It's just including the Planck data plus large-scale structure data. And you can see that there is a preference for a lower S8, which is important. The model does accommodate a better agreement with large-scale structure data even without putting in those direct measurements or without needing a large abundance of these new species. So that's at least a positive message. In sort of we're still finalizing these results, and one of the things that we're hoping to see is, you may be worried that this is a 5-parameter model, so it takes lambda CDM from 6 to 11 parameters. Does it really do a better job of fitting data beyond how much you would expect from just adding new parameters? This is one of the main questions we're trying to answer. It's complicated because it's really hard to get a good analysis with this many parameters, but that is something I'm hoping will become very apparent in the next week or so, and we'll sort of have an update soon, so please look out for it. that's all I had to say. I might have talked a little faster than I was supposed to, but I'm happy to take questions if anyone has them.
Thank you very much, Itamar. Just a quick question. So you have dark radiation here, and presumably one dark particle decays to another. That would be the source of it. There are constraints on the degrees of freedom of anything radiation based on the CMBs. I assume that it's consistent within that.
Yeah, exactly. So the sort of point of this model is to say if you just have a dark radiation species, it's heavily constrained, something like 0.3-ish in the, effective number of neutrino species. But when you have this step introduced, it begins in a lower abundance, and then sort of around that redshift, it steps up because of these decays. That alleviates some of that pressure. But I mean, if you look at this distribution, the constraints coming from before you add in the priors on S8 and H9, when you're just looking at the Planck data, for example, the blue curve, it's already constraining it down to something like 0.5 or 0.4. So it's not very different, at least at, let's say, at 95% confidence. But it is a little bit, it gives you a little bit more breathing room than, say, just a regular extra dark radiation species.
Please.
I have a question. So, in addition to 5 years of freedom of however many you had, I remember you said earlier that Kennedy was problems with coincidence, embedding it in particle physics models. Is there any reason to expect dark radiation to do any of this behavior at recombination roughly at the EV scale?
Yeah, I mean, that's a great question, right? So this doesn't address the coincidence issue there, but some of the things we've discussed is how it could be addressed. So the papers by Allali and collaborators that came up with this model, they focused on this sort of two species, a scalar and a fermion, and one becomes massive and then decays into the other. You can get the same phenomenology in other ways. So I don't know, for example, some other kind of phase transition instead of just something becoming massive and decaying, maybe an actual phase transition in the sector or something. And that provides some space to see, well, maybe this has some relationships to, pieces of the standard model that are going to explain this coincidence. It's not a very good answer because we haven't figured it out yet, but that's a hope that, right? So the implementation that you're looking at in these plots is just the phenomenology. It's not tied down to the particle physics, but it has a good particle physics explanation, which is why we like it. But if you come up with a different particle physics, which does explain the coincidence problem, this phenomenology will still apply, which is a nice feature.
Well, one aspect of the coincidence, it's the matter radiation transition, isn't it?
Yes, or around.
So if you had a physical reason to believe that the matter radiation transition was related, this decay was related,
this would be a great way to do it. I mean, in this particular model from these authors, it sort of depends on either the mass of this species or some combination of the mass and the temperature of the sector. So it's kind of hard to say why that would be related to matter radiation equality when this thing barely talks to those species, but yes, it would be nice.
Okay, any other comments? If not, let's thank Itamar.
Thank you.
Hi everyone, thanks for having me. So today I'm going to talk about my latest paper written with Avi entitled Interstellar Meteors are Outliers in Material Strength. So just for some introduction, the first interstellar meteor larger than dust was CNEO's 2014-0108. We abbreviated IM1. We discovered it in the CNEO's Fireball database, which is a U.S. government-maintained Fireball database, and it struck off the coast of Manus Island, Papua New Guinea, on that date. And we originally flagged this in 2019, but only in 2022 did we receive confirmation from the Department of Defense that the underlying data was within the error boundaries or uncertainties that we had assumed. And so, as a result, this discovery was published in AppJ after the DoD confirmation. And what's interesting about this object is it had a very high excess speed outside of the solar system, 42 kilometers per second outside of the solar system. So as a result, its heliocentric speed when it hit the Earth was very high, something like 60 kilometers per second. And it also, very far from the solar system, was moving quickly relative to the local standard of rest, average of local stars, at about 60 kilometers per second. So there's the orbit. And in this new paper, we introduced this secondary candidate. It is yet unconfirmed, but it's also in the CNEO's Fireball database. It struck the atmosphere off the coast of Portugal. Its mass is a lot larger, about an order of magnitude, but its kinematics are slightly less extraordinary. It still, has a high excess speed far from the solar system, about 26 kilometers per second, and is still far away from the local standard of rest. And the reason why the study of interstellar meteors is important is because we only have two objects, Oumuamua and Borisov, that we've seen in space with clearly hyperbolic trajectories. And so we're very much in the small number regime, and so any new object tells us a lot about what we can look for next. So about the material strength, we can estimate, and get some sense of the material strength of these objects, given the fact that as a meteor travels through the atmosphere, it experiences friction due to the air. And that dynamical pressure goes as rho v squared, where rho is the density of the air and v is the relative speed. And as a result, the dynamical pressure corresponding to the peak power in the light curve, which were also released by the DoD, describes some sense of the material strength of the meteor. And this came out to, so in this upper right-hand plot, we see in navy blue the light curve for IM1 translated into total power as a function of ram pressure, and then the same for light blue IM2, the second candidate. And we get 194 megapascals for the light curve peak for IM1, 75 megapascals for IM2. And so in this paper, we put those numbers in context. We did this calculation for all 273 fireballs in the US government database. And we get this histogram. It looks roughly like a log normal distribution with a mean at 0.65. This is in log 10, base 10, and a sigma of 0.47 megapascals. And interestingly, IM1, the confirmed interstellar meteor, is all the way over here, and IM2, the unconfirmed interstellar meteor, is number 3 in terms of material strength rank. And just note that that green line is 50 megapascals, and that's the typical iron meteor, which is the strongest known class of meteorites that have been found. 5% of modern falls. Most are stony or icy, which are on the order of a few megapascals, as you can see here. And so they're ranked first and third in terms of material strength out of the 273 fireballs in the CNEO's catalog. So you can ask, well, if they were randomly sampled from the same material strength distribution, how unusual would it be? Random sampling gives us about 10 to the minus 4. And then, if you consider these to be samples of this log normal distribution, gives you something more of the order 10 to the minus 6. The point is that if the second interstellar meteor is confirmed, this points to, perhaps interstellar meteors come from a population with a characteristically higher material strength than meteors originating from within the solar system. We can also get a sense of the kind of abundance we're talking about. if you adopt a background population on random trajectories drawn from an isotropic distribution in the local standard of rest, you can adopt some implied rate relative to, that comes from your survey parameters. And then you plug in the speed outside of the solar system, the radius of the Earth, the escape speed from the Earth's position in the solar system, and you can then estimate the number density up top. And given the CNEO's survey has been operating at a global high cadence for about a decade, you can plug in a decade, once per decade for gamma, and that would imply an ambient local abundance of about 2 times 10 to the 6 per cubic AU and 3 times 10 to the 6 per cubic AU for IM1 and IM2 respectively. And this plot just shows what happens if you add the associated Poisson uncertainties to 95th percentile confidence for single detections, having to do with Poisson processes and the uncertainty in the rates as inferred from one detection. And then the y-axis shows the number per star given the local stellar density. And here's just a little summary of the properties that I discussed. And then finally, you can get some estimate of the mass budget implied by these objects. So local stellar mass density is 0.04 solar masses per cubic parsec, and then interstellar medium is about 0.03. And then if you look at solar metallicity, all refractory elements, so metals and silicates, are constitute about 0.3% of all mass at solar metallicity. And so we can estimate the local budget of refractory elements in stars and dust as being around 70 Earth masses per cubic parsec. And again, if we go back to abundance and we plug in once per decade, if we make that guess, then IM1 and IM2 respectively imply local abundances of about an Earth mass per cubic parsec for the confirmed object, and then 25 Earth masses per cubic parsec for the unconfirmed one. And so that would be about 2% and 36% of refractory element budget, respectively, in meter scale interstellar objects. And so this is just to get a sense of the scales that we're talking about. Of course, we have those Poisson uncertainties. But if the second interstellar meteor ends up being confirmed, that latter value seemingly defies a planetary system origin. And so, we've started looking into other possible origins for interstellar objects, including supernovae, ejecta, et cetera. But this is really why one of the many reasons why it's so exciting. So, as Avi mentioned at the beginning, we are currently planning an ocean expedition. We're going to try to find little pieces of IM1 on the ocean floor, and then go from there. And we'll keep you updated with what we find. But thank you.
No questions.
Amir, so my sense is that the column of ISM or even molecular cloud that you pass through is pretty small compared to the atmosphere once you reach it. But is there any selection effect where particularly fast-moving objects, the weaker ones would be destroyed, sort of thing, or is it just not even close orders of magnitude?
Yeah. So some other authors proposed that, and it's actually a very important thing to check. And so we looked at the numbers, and you're right, the column density is just orders of magnitude too low compared at what happens when you're arriving at the atmosphere. So unless there's, it would have to be some really exotic effect with cosmic rays transferring a huge fraction of their energy into evaporating objects, but it seems quite unlikely.
So they're kind of untransformed by that time.
Yeah.
It looks like that.
Just a matter of column density, Morgan. So for a meter-sized solid density object, there is much more column than in the interstellar medium.
Yeah, I want to follow up on Morgan's question about detectability and selection effects. with respect to the error bars that I didn't see present on any of those numbers. So I assume that the velocity you're getting is mostly from the actual fireball track. And if something is soft and burns up immediately, you probably have much bigger error bars on its velocity and its sort of out of solar system velocity. So is there any selection effect that's causing them to be too significant?
Yeah. So, so we do have some sense of what, at least an upper bound of the uncertainties on the speed for IM1, and then we also have just in general some of these CNEO's fireballs, some of the fireballs in the catalog were also detected elsewhere and by other sensors, Chelyabinsk, etc. And both are in sort of pretty close agreement. The typical error is of order a few kilometers per second, and so that doesn't end up being a huge. It doesn't end up changing the result in terms of the order of magnitude of the ram pressure that we're getting, but certainly those numbers should not be taken as gospel. They're just more of a sense of, we know it's not 1 megapascal, we know it's not 10, it's of order 100, etc.
Would you like to comment on the seismometer data, because we didn't mention
Oh yeah, so we're also working on a paper right now in which we actually found seismometers throughout the Pacific Ocean that picked up the first interstellar meteor, IM1, exploding in the atmosphere. And so as a result, we are basically fitting a model that has the elevation and the location and all of these other parameters for IM1. And the point is that we can use this seismometer data to get a much better handle on where exactly this fireball occurred, because the government only released the data to the first decimal point in longitude and latitude. And so we do have other data that we're analyzing right now.
I'm curious about how you're planning on differentiating the material from IM1 from other just stuff that's in the ocean.
Yeah. So it would have to, first of all, iron meteorites are fairly rare, only about 5% of falls. But the real differentiation is going to, we're going to be looking for differences in key isotope ratios. And since a lot of the fragments from IM1 will be ablation spherules, you'll want to look at things like chromium isotope ratios or other metals that you really expect to, one, survive and preserve that history, but also be different in other planetary systems.
The thing to do is to check against some other area of the ocean in that vicinity just to compare and see that it's unusual.
Yeah.
And that's a very good point. Okay, if there are no more, is there more? Charles?
Just a quick one. Do you know how complete the fundamental databases that the military is running is? Do they get 90% of the fireballs or 50% or do you know that?
Yeah, so they claim they try to publish everything above, the majority of fireballs above 0.1 kT. And it seems to, there is no, unfortunately, scientists don't have access to any system that rivals the satellite constellation that the DoD has, but the number of fireballs as a function of energy seems to be in line with estimates of the overall rate of small body impacts on the Earth done by smaller surveys.
Just to explain what Amir was saying when he said KT, for those people in the audience that did not live through the Second World War, it's kiloton of TNT, which is a measure for nuclear explosions. The last time an explosion took place was in Japan, as you know, twice. And so meteors like this one released about a few percent of the Hiroshima atomic bomb. And a meteor of the strength of the Hiroshima atomic explosion hits the Earth once a year. Many people don't know that. Every year there is an atomic explosion in the atmosphere of the Earth. Did you know that? That's quite remarkable. It's an object of the size of IM2 roughly, which is similar in energy to Hiroshima.
But thankfully those objects break up very high in the atmosphere typically. The issue with Hiroshima is they dropped it at 1 kilometer.
Well, it was intended. But, But the other thing I wanted to mention is that by now we have sort of a sense of what the government, why does it take so long for the government to release just a simple number like localization? You know, we have GPS systems that taxi drivers use and they tell them where they are within a few meters. And here we're talking about 10 kilometers. So why is it the government is so reluctant to improve the localization beyond, smaller than 10 kilometers when taxi drivers have a few meters localization? The answer is they have to go through a very tedious process of layers of bureaucracy, making sure that if they give smaller error bars, adversaries will not be able to use those error bars to infer the type of sensors being used by the government. And that takes a huge amount of time and bureaucracy. So that's why it takes them so long, years usually. That was true also of the gamma ray burst in the early 70s, which was another discovery the government made that later on the astronomy community benefited from. So the government is getting good data that is useful for astronomy, but it just takes them a long time to release anything. That's all. Okay, let's thank Amir again.
Seems to be running out.
Yeah, he wasn't on the list. But he gave that. Sex official.
Right, that was
So they ought to be doing this thing. Wow, well, they do that. I mean, was at Livermore years ago and had a few clearings to people who did supernova models because they have the data that allow them to do those supernova models.
good. So it's just like
Okay, fantastic. So this is going to be a bit of an experimental format, so we'll see if it works, and we'll even involve a bit of live programming, which I'm told you should always avoid doing. So we'll see how this works. So just to kind of set the scene and context here, especially for anyone that wasn't able to see my talk earlier, everything that we know about exoplanet atmospheres is fundamentally changing at the moment because of the sheer increase in quality of observations that we're now obtaining from the JWST. What I'm showing here is a summary of 4 separate observations that we released early this year. So the press release was in November, and these papers will have been accepted for publication in Nature and should be coming out next month. And what we're seeing here is, even by eye, from the optical all the way through to the near infrared, multiple absorption features of molecules like water, the first detections of carbon dioxide and sulfur dioxide in an exoplanet atmosphere, and also things like alkali metals. And this poses an interesting question when it comes to the theoretical process of how we extract inferences, how we can not only detect molecules but measure their chemical abundances and other atmospheric properties. So if we zoom in just on the one in the bottom right, for example, you can see here that this model fit to the observations, which was just one of the very first ones that we concocted. Even by eye, it's not doing as good a job as we would like. There are some areas where there are quite substantial residuals, like here and here, so you're looking at a reduced chi-squared of about 3 or so. So the main area that I work on is a process called atmospheric retrieval, which essentially is Bayesian model fitting and comparison. And that's what I want to show off today, demonstrating an open source code to solve this problem that was just published in the Journal of Open Source Software about 2 weeks or so ago. So yeah, let's try and fulfill the promise of fitting a spectrum in less than 10 minutes. So what I'm going to demonstrate here is essentially the process of fitting a spectrum of the kind of quality that we have been obtaining until in the pre-JWST era, so Hubble-like quality spectra. So let's imagine that one of our colleagues sends us a spectrum that looks like this, where even by eye, just looking at a near-infrared spectrum of this fictional planet, but lots of hot Jupiters do look like this, you can see what looks like 2 distinct absorption features here in the near-infrared. And this is around about the same signal-to-noise ratio that we routinely see with the Hubble Space Telescope. So at this point, you can consult your favorite theorist, or you can chat with your good friends at like HITRAN to see what kind of molecules may have signatures in this particular wavelength range. And these are well computed from either laboratory measurements or from first principles quantum mechanics. You have databases of absorption features of different molecules. And so you might notice, for example, that at 1.4 microns that we're looking at, we expect to see a strong feature from water vapor absorption. So this is a good candidate to include in the atmospheric fitting process. So at this point, you can even, maybe you ask another colleague who happens to have some visible wavelength data that you can then add to extend your spectrum down to shorter wavelengths. And now we're ready to go with the process of trying to fit this spectrum and obtain atmospheric inferences from it, which I hope with my code Poseidon I've been able to make such that you can do in just a few lines of code. So the first step is to encode your model assumptions, which here we're just going to make a toy model that is hydrogen and helium dominated and has water vapor as the only trace species. And we'll assume there are no clouds and that the temperature of the atmosphere is just constant with altitude. So first step is to define your assumptions. The next, to set your priors. So what is the range that each of these atmospheric properties can span? So if we know the equilibrium temperature of this planet is about 1000 Kelvin, you might want to say let's fit every temperature from 400 to 1600 or so. And you can also specify the range of water abundances that you allow and the uncertainty on the planet radius. So we've defined the model, the priors, and at this point we can now read in the database of all the quantum mechanical transitions of the water molecule and then interpolate that onto the pressure and temperature grid that we want to explore. That's now done, and with that we can now run the model fitting process. So this will take about 5 minutes or so I can give kind of context on what is going on in the meantime. Essentially this is it's using a code called multinest, which is a nested sampling approach. It's a very similar idea to a Markov chain Monte Carlo. Essentially the idea is a number of points are scattered throughout the parameter space, which in this case is just a simple 3-parameter toy model, defined by the radius of the planet, the temperature, and how much water vapor there is in the atmosphere. Then in this case, 400 models are computed at the same time. You then compute the value of the likelihood function, which kind of looks like e to the minus chi-squared. And then you eliminate the point with the lowest likelihood, rescatter that in multidimensional ellipsoids that are drawn around the likelihood surface, and iteratively map out the entire parameter space to then establish what the range of these parameters are that are consistent with the given set of observations. And we'll see some nice summary plots in about 4 minutes or so when that process is done. So in terms of the physics of what is actually happening here, essentially, and I do actually have a plot illustrating that. So what we're trying to solve for here is to produce a theoretical model of the wavelength-dependent absorption, so the fraction of starlight that is absorbed by the planetary atmosphere as a function of wavelength. So this is done by solving the equation of radio transfer across an array of 100 rays that are injected into the planetary atmosphere, and then you essentially integrate along the line of sight to calculate the fractional absorption across all of these different rays, and then integrate them together over the kind of projected surface of the planet to then work out the overall predicted absorption. So, okay, we're now about halfway in the convergence process. It'll take about 9,000 model evaluations to map out this simple parameter space. So we're already about halfway there. So at this point, I'm just going to stop for a moment for the next couple of minutes in case anyone has any questions to like invert this a little bit until the retrieval process is finished. Yeah?
So this is super cool. I was curious, given your earlier talk, you have a very high-dimensional model in principle with this sort of raster on your planet. And my understanding is that the implemented sampling has very poor behavior as you go to very large numbers of parameters. So I'm curious, what is the runtime like, at least on a personal computer, when you're using the best model you would ever want to drive realistic big fitting?
Yes, so the highest dimensionality that I've gone up to is 42 dimensions. And that took a while. That was like a couple days or so on like a 12-core cluster or so. So on a personal laptop like this one, and this is only running on one core because of a limitation of Jupyter notebooks. On a multi-core laptop, you can do retrievals even of JWST quality data if you're willing to wait a day or so. And it's so yeah, you're right. The runtime kind of exponentially scales with the number of parameters with these kind of algorithms. So typically, you don't want to do much more than 30 parameters if you want to be able to run one of these model fitting procedures in less than about a day or so. Yep. I mean, I did try to see if ChatGPT could help me with any JWST proposal, and it's like gobbledygook that it spits out. Like it says, I said, can you write a proposal to tell me how to detect ammonia in the next planet atmosphere? And it says, okay, observe a transit of a planet. I was like, okay, this looks pretty good. And that will then give you thermal emission at high resolution using the NIRSPEC instrument on the Hubble Space Telescope. And I was like, it's just taking buzzwords and just combining them together. So I don't think we're going to be out of a job like immediately because of ChatGPT. Oh, great. Okay, it's starting to finish now. And but what we have found it is really good at is just text editing. So if you give it an abstract for a paper, like a Nature paper, that's just 50 words too long and tell it to make it more concise, it's pretty useful at that. So yeah, maybe if you've already written your proposal, it might be able to help improve the English at least. Yeah?
Incremental effects like line spread functions and sampling over those sorts of things. In a fully Bayesian sense, you should marginalize over all of that. Can you comment on how important that is for the JWST spectra that you're looking at, for example?
Yeah, absolutely. So one of the considerations on the instrumental effects for JWST spectra are like relative offsets between the data sets that you can absolutely include in a retrieval context. That's the most common instrumental effect that's marginalized over. But yeah, in general, we're assuming, and actually a lot of the work we're doing at the moment is a consistent analysis from the light curves of all of these data sets together to try and really make sure that all the instrumental effects are being accounted for systematically before we get to the Bayesian model fitting stage. But we'll still include the offsets just to kind of verify.
But the line functions are fixed?
Yeah, in most of these cases, the likelihoods are assuming independent Gaussian distributed error bars, but you could in principle include like a GP to account for like red noise and correlated effects there, and people are looking into that. Okay, so moment of truth, let's see what this looks like. Yes, fantastic. Yeah, actually, let's see what it. Yeah, 4 minutes 45 seconds. That's not too bad for this toy model here on one core. So we can see here that the model's not perfect. I mean, it's reproducing these two water features here, but there's still considerable scatter at the shorter wavelengths. It's not quite being captured. And here's the corresponding corner plot showing like that. That's a quite decent measurement, about what, 1/10 of an order of magnitude or so on the water abundance. But if you look at summary statistics, the reduced chi-squared is still about 3 or so. That's mainly driven by this scatter at the shorter wavelengths that isn't quite being fit. And although I won't run an improved model here, I do have the results saved from a 6-parameter model that then takes about 15 minutes to run. In that what was missing was actually sodium and potassium absorption in the planetary atmosphere. And if you add that, you can then see that we get a much better reproduction of the overall spectrum. Reduced chi-squared is now actually overfitting a little bit. Because if you include a molecule that is not actually there, then you will just derive an upper limit from the probability distribution. But yeah, so there you go. That's the process that we're trying to go through to fit observations. And for real GWST observations like this one, the corner plots look a little bit more messy.
Wow. Well, we had the question period done already, so let's thank Ryan and all the others.